Okay, so now we're going to do lesson 19. I'm going to try to keep this to 20 minutes or so because the other video was about 11. So 25 minutes so that you can have the 10 minutes to do the quiz and we'll stay within the realm of a normal 15-minute class. So let me set a timer for 25 minutes. Okay, so lesson 19 is about polyprotic acids. So the word polyprotic, this means many protons. Okay, we know that it's polyprotic because of its chemical formula. It'll usually have a 2 or 3 after the proton when we're looking at the acid. So what we're going to do first is we're going to look at the ionization constants. So these are the capital K's of conjugate acids and bases. Now, problem number 1 says write the equilibrium constant for the reactions below. So we're looking for the expression. You can see here we have acetic acid losing its proton to form acetate, and then we have acetate reacting with water to form acetic acid and OH. So this would be acetic acid acting as an acid, and this would be acetic acid acting as a base. Therefore, we have a Ka and a Kb. One might say that these are reversible versions of each other, but they are a little bit different because of the component of water. So if we think about like reversibility, it is a reversible process, but there's different reactants and product species. So we're going to write Ka and Kb expressions a little bit different. Now let's start with Ka. It's still going to be products over reactants, so we're going to have 2 products in our first one and then 1 reactant. Let me zoom in. So that's going to give me H plus times the acetate ion, and remember that H plus and hydronium are used interchangeably. If I had had water as a reactant, it would have been written as hydronium on the right and not just proton. And I'm going to divide that by my reactant, which is my acetic acid. And now I'm going to write my Kb, which is going to be products over reactants. So it's going to be acetic acid times hydroxide divided by the acetate ion. Okay, so those are my equilibrium constant, and this should say expressions for these 2 reactions. Now, it says these equations can be combined to give a relationship between Ka and Kb. And so I'm going to combine Ka and Kb by multiplying them. Because I'm multiplying the constants, I can also multiply what the constants are equal to, which are the expressions that we wrote above. And so I'm just simply transposing. Oh, that looks messy. Sorry, guys. Okay, bracket OH go get a snack if you want. Sorry, I have Anderson at home right now. Hey, and so I've written everything out, and now I'm simply going to cross out what's on the top and bottom that's the same, and what that's going to leave me with is Ka times Kb is equal to these 2. Just go get a snack for right now. Go get a bag of chips. Lord help me. We may not make it through Corona. And so if you remember back to lesson 18, I think that was this lesson. Nope, it was lesson 17. We had a formula in the very, 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 very beginning, which I wrote on the board, but luckily it's here, which stated that the concentration of hydronium times the concentration of hydroxide was equal to Kw, a unique constant. And so lo and behold, when I take these 2 equations, multiply their Ka and the Kb, I also say that that's equal to Kw, which is also equal to the Kw constant. So all four of these things are equal to each other. Ka times Kb is equal to this, it's equal to Kw, it's equal to that. Okay? Really useful relationship that we're going to use. Okay? All right. So let's look at some specific examples of how we might use this. So in this case, we're going to look at polyprotic acids. These are when we have acids that are able to donate more than one hydrogen molecule. So we have H2SO4, you might have H3PO4. Those are just a few examples of polyprotic acids. If it was H2SO4, we would call this diprotic, and H3PO4 would be triprotic. Okay. So what we know is that these acids are going to ionize in multiple steps, losing one proton at a time, and because they're going to lose one proton at a time, they're going to have their own unique Ka values, Ka1 and Ka2, to show which step we're on. Okay, so if we look at H2CO3, this is carbonic acid. It can lose one proton to form bicarbonate ion, and then bicarbonate can lose a second proton to form carbonate ion, and they're going to have their own unique Ka1 and Ka2 values. Now, problem number 2 says calculate the pH for a solution of 0.23 molar of sulfuric acid. This is a strong acid, so what this means is that when I take H2SO4 and I put it in water, it is going to give up its protons to form H3O plus SO4 2 minus. And now I need to balance my equation because I have not accounted for everything. So I'm going to put a 2 in front of the H2O3s, which gives me 6 protons on the left and only 4 on the hold on, let me make sure I got this right. So I have 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So I'm going to add a 2 in front of the water because each water is going to take 1 proton, giving me 2 hydroniums and 1 sulfate ion. So I'm starting with 0.23 molar of sulfuric acid, and all of this is going to become hydronium and sulfate because it's 100% ionization. There's no equilibrium, no ice table involved. So in this case with the strong acid, it's going to be pretty straightforward. It's going to be 0.23 molar of H2SO4, and for every 1 mole of H2SO4, I'm going to form 2 moles of hydronium because I want to solve for pH, and this is my pH component. So I get the numbers 1 and 2 from my balanced chemical equation above. That's why it was important to balance it with the polyprotic acid. If it only had a single proton, it's 1 to 1, so it doesn't have an impact on the pH, but when it's polyprotic, it will. This means my concentration of hydronium is going to be twice as much, so it's 0.46 molar. And then to solve for pH, I'm going to plug it in to the pH is equal to the negative log of the concentration of hydronium, which is 0.46 molar. And when I solve for that, I should get a pH of 0.34. Okay. So when it's a strong acid, make sure, and it's polyprotic, make sure to mass balance. If it only has 1 proton, so HCl, HBr, HI, HNO3, HClO4, it's 1 to 1, so we take it for granted and don't necessarily worry about mass balancing, but when it's polyprotic, we need to make sure we do. Now, if we want to calculate the pH of a solution of a weak acid, we do have to worry about ice table. Okay, we have to worry about equilibrium, So we're going to have to do something a little bit unique. So in this case, it says calculate the pH of a solution of carbonic acid. It gives you an initial concentration and the Ka values. And so I'm going to write out the balanced chemical equations. They are above because it's what we started with on this particular lesson right up here, these. But I'm going to rewrite them because I want to put water in the expression. And that's Ka1. And then my second one is going to start with my bicarbonate ion and going to leave me with a carbonate. Okay, and then I have Ka2. Now I need to calculate the pH of the solution, but the problem is I have two pH contributors. So what I have to look at is which of these equations is going to dominate, because whichever equation dominates, meaning it's the most favorable, the one that goes to the biggest completion, that's going to be the one that's going to determine the pH. And the other one may affect it a little bit, but not nearly as much as the equilibrium that's found in the majority. So to do that, I have to compare my Ka values, because remember, Ka is an expression of products divided by reactants. So the more products I have and the more products I have, the fewer reactants that are left. Therefore, as the reaction proceeds to the products, the Ka value gets larger. If the reaction does not proceed to the products, then the Ka is going to be small, and that tells me which one is going to be the biggest contributor to pH. The one that has the bigger K value, because the bigger K value means more products. More products means more hydronium. More hydronium means more of an impact on the pH. So when I'm comparing Ka1 and Ka2, I can hopefully see here that Ka1 is greater than Ka2. Therefore, the only contributor to pH that I'm going to worry about is the first step. This is the main producer of H3O+, and it is the predominant reaction. Therefore, I only have to worry about that expression, okay? So with that information, I'm going to set up my ICE table yet again with my now predominant reaction. Now say that Ka2 was larger than Ka1. Well, then I would be working with Ka2 at this point and not Ka1. So I know that my initial concentration of carbonic acid is 0.23. I'm starting off with 0 of my others. My reaction, just like the other ones, is going to proceed to the right to produce my products and consume my reactants. I have my equilibrium values, and now I have to determine, is my Ka going to be significantly larger? So I'm going to take 4.2 times 10 to the negative 7th, multiply that by 1,000, 642 times, and you may have done this math in your head, and that's great, but what I see is that the Ka times 1,000 is still much smaller than the initial concentration, so therefore my minus x is going to cancel out. And so now I'm going to plug everything in. Ka1 is equal to x times x, which are my products, divided by my reactant amount. I only have one, which is equal to my 4.2 times 10 to the negative 7th. I'm going to rearrange, solve for x, and I see that my x is equal to 0.00031 molar. This is the main contributor to the pH. It's also the value of my hydronium concentration. Therefore, I can plug it directly into the pH as the negative log of the concentration of hydronium. And I should get a value of pH is equal to 3.51. This should make sense because this is a acidic solution, therefore I would expect for it to be a pH of less than 7, because that is what we expect for acids. Whether they are weak or strong, it's irrelevant. The pH should be less than 7. All right, so now we are faced with another problem which says to solve for the equilibrium concentrations of all species present in a 0.85 molar solution of phosphoric acid. Okay, and so this is kind of a tricky problem because as you may see, it's not right in highlighter, phosphoric acid has 3 protons. So what this means is I'm going to have 3 equilibriums expressions and 3 Ka values. Each time the acid is going to give away one of its protons until at the very end it no longer has any more protons to give away, which is going to leave me with a, let's write this the same way, leave me with a phosphate ion only. Okay. Now the Ka values are not values I expect you to memorize or know. That would be a little unreasonable. But what we do see here is that as we go further on in the sequence of donating protons, the Ka values become smaller, which means that the biggest contributor to pH is the donation of the first proton. The second and third step may donate some, but not a significant amount. So believe it or not, I'm going to have multiple things I have to solve for. I'm not going to solve for water, but what I need to know is this concentration, this concentration, this concentration. I need to know the hydronium concentration, and the only other one that's going to be unique is this one. So I'm going to have 1, 2, 3, 4, each of the phosphoric acid derivatives losing a proton each time, and then hydronium. So let's set up our first ice table. I know I need to set up an ice table because this is a weak acid. I know that because it's not one of my strong acids and it has Ka values. It tells me I'm starting with a 0.85 molar of phosphoric acid, none of my hydronium or conjugate base. Reaction shifts to the right, just like every other one. And I'm left with something that looks very familiar to me on the equilibrium row. So now I'm going to take the Ka2 and if I multiply, Ka1 and multiply that by 1000, what you can probably see is that the value is not going to be smaller than our initial amount. What this means is I cannot get rid of the minus x. It has to stay. So it means I'm going to be doing a quadratic. I'm not going to solve the quadratic for you again because we've done, 3 or 4 at this point. So this would be a good opportunity to practice setting it up. Okay? So at this point, you'll do the quadratic. I'll write down what my A and B and C values were so that you can see them. So my A came out to be 1. My B came out to be 0.0075, and my C came out to be negative 0.006375. Once you do the quadratic, the value that you get is 0.076 molar. So every x is equal to that. So my plugging them back in, my value here is going to be, let's write a different color, 0.774 molar. That's the concentration of my phosphoric acid, my hydronium, and this one, okay, the conjugate base. So now, when I'm looking at my next ice table, I'm going to pick to go ahead and work with the second one, which is right here. So I'm going to start off with my H2PO4, so kind of starting off where I ended last time. And leaving me with phosphoric acid with only one proton. So in this case, I know my equilibrium value is 0.0762, 0.0762, and what I don't know, sorry, I don't want to put an arrow there. What I don't know at equilibrium is what this is equal to, okay? Because these are all equilibrium up here, there's still equilibrium down there. So I'm going to take my Ka2, and I'm going to do x times 0.0762 divided by 0.0762, products over reactants, is equal to my Ka2. You might see that these are going to cancel each other out, meaning that x is equal to 6.3 times 10 to the negative 8th. So what that means is x is equal to 6.3 times 10 to the negative 8th molar, which is the concentration of HPO4 2-. So I know the concentration now of H3PO4, H2PO4-, I know hydronium, and now I know HPO4 2-. What I don't know is the last PO4 3-, the last conjugate base. So I'm going to set up another ice table with my third equation. Now the tricky thing about these ice tables is they look a little bit different than what we've had in the past because they, my lines got mixed up in my head, because we don't have initial values for all of them, but the nice thing about the ice table is it's really just meant to help you organize what you have. I know the concentration of my HPO4 2- because I just solved for that. I know my concentration of my hydronium because I solved for that up in the very first ice table. And the only thing I don't know is what my PO4 3- is equal to. So I'm going to set this up as Ka3, 0.0762 times x divided by my reactant value. Set that all equal to Ka3. Now remember, these are not values to memorize. I would give you these values on a test, so I'm not expecting you to memorize them anyway. And the x value that you should get is 2.98 times 10 to the negative 19th molar, which we would expect because it's got a very, very small Ka value, which means there's not a lot of that product anyway. So in the end, now we have the concentration of H3PO4, hydronium, and H2PO4-. We got that from the first ice table. Then we used that information to solve for the concentration of HPO4 2-, which was just really equal to its Ka2 value. And then we used all that information to solve for PO4 3- and used the third expression to solve for that. Okay. All right. That's a lot. I would recommend watching that again, making sure that you are fully confident in that. The nice thing about having this recorded is that you can watch it as many times as you want, especially if you start to miss me. All right, so acid-base properties of salts. When an acid and base react, the ionic compound that forms is called a salt. Remember, acids and bases reactions form salt and water. And then these salts can then further react with water to form something that's basic, acidic, or neutral. Okay, so something that is a neutral salt is formed between a strong acid and a strong base. So I don't know if I'm getting these backwards, but HCl plus NaOH forms NaCl plus water. This is a neutral salt. A basic salt would be something that's formed between a strong base and a weak acid. Okay, so this would be something like sodium carbonate plus water. Okay, this is a basic salt. An acidic salt is something formed between a strong acid and a weak base. I really don't like this one, but it's all I can think of right now. Like ammonia, this forms NH4 plus Cl minus. Okay? All right. If the salt is made from a weak acid, we'll finish this last bit up. A weak acid and a weak base, so something like carbonic acid and ammonia, the acidity of the base will be determined by the relative Ka values. Okay? So if Ka is greater than Kb, it's acidic. If Ka is less than Kb, it's basic. And if Ka and Kb are about equal, it'll be neutral. So we really have 4 options: strong acid, strong base, weak acid, strong acid, weak base, weak and weak acid base. So the first thing to do is identify, and we'll make this our last thing that we'll do today. Identify the nature of our acids and bases, our salts, and then determine where they came from. So if we're looking at A, this is NH4ClO2, and if we're thinking about the ions, they're going to break apart like this, ionic in solution, so they're going to become cations and anions. We know that NH4 comes from ammonia, which is NH3, it's a weak base, and ClO2 minus comes from HClO2, which is not a strong acid, so therefore it must be a weak acid. So this is its conjugate base right here, and this is its conjugate acid right here. So because they're weak and weak, we need to compare the Kas and the Kbs. In this case, the Ka is equal to 5.6 times 10 to the negative 10th. Kb is equal to 9.1 times 10 to the negative 13th. In this case, Ka is greater than Kb, which means that this salt is considered to be acidic. Okay, so that's this last rule at the bottom. Now when we're looking at B, B is CaBr2. If we break those apart, let's make it similar. Calcium 2 plus, Br minus. Calcium, it may look familiar to you to come from CaOH2 and Br, HBr. So this is a strong base, this is a strong acid. So this is the first example that we had where the strong acid and the strong base react to form a neutral salt. So they're essentially going to cancel each other out and neutralize. If we look at C, C is K2CO3. This breaks apart into potassium and CO3 2 minus, which comes from potassium hydroxide and carbonic acid. So this is a weak acid, this is a strong base. If we go up to the top, when we had a strong base and a weak acid react, the salt would be basic. So the salt is basic. In D, we have NaF, sodium fluoride. This is Na plus, fluoride minus. The sodium comes from NaOH. The fluoride is going to come from HF. This is a strong base, weak acid, very similar to to C, the one we just did. So making this also a basic salt. If we look at E, E is lithium chlorate, lithium plus, ClO4 minus. This comes from lithium hydroxide and comes from perchloric acid. this is a strong acid, and lithium hydroxide is a strong base, making this salt neutral. Okay. All right, looking at F, let's go up here so we can see F. We have C6H5NH3NO2. The reason why I wanted to do this one is because it's kind of confusing. On this one specifically, this is a derivative of like the ammonium ion. Instead of having 4 protons, it's going to have 3 protons and a R group, which is R can be anything carbon based. A methyl, ethyl. This is a example of a benzene, so it can be any sort of derivative of that. So this is going to come from some sort of ammonia derivative, which is a weak base, just like ammonia is, and then HNO2, which is a weak acid. So we have to compare the Ka and the Kb values, and in this case, oh, I didn't write down the Ka values. So this one we'd have to compare the Ka and the Kb values to determine, but I don't have them on my paper right now, and I don't want to keep y'all any longer. But in my announcement with this one, I will post the answer. For G, this comes from NH4. It's ammonium bromide, so it comes from NH4 plus, Br minus, which comes from ammonia, which is a weak base, and HBr, which is a strong acid, making this salt acidic. Okay, and the last one, you may be able to see it's sodium iodide, which is Na plus, I minus, comes from NaOH, and HI, strong base, strong acid, makes for a neutral salt. Okay, so I recommend working about it this way, making sure you can identify where it's coming from, and that way you will be ready to go. You have to think about what it forms in water, meaning cations and anions, and then where those cations and anions come from, and that's how you predict the acidity, basicity, or neutral nature of the salts. You need to know these, okay? I'll try to find another good video on YouTube or Khan Academy to support what we learned in this video, but make sure at this point that you take or you have taken the quiz that was supposed to be taken on Monday so that you're not behind, okay? No excuses. Watch this video again if you're confused about any of these equilibrium expressions for polyprotic acids, or feel free to email me.